and how to calculate pressure requirements. To explain how, we'll use a practical example. Auntie Flo's land has a steep hill. Her rainwater tank is located near her house. She has positioned her pump in the best spot, right at the base of the tank. From this point, she has 50 meters of pipework to the furthest sprinkler in her yard. This sprinkler is located at the top of the hill, which is 4 meters higher than the pump. The pipe she is using is 3/4 inch in side diameter, and she requires a flow rate of 45 liters per minute. The sprinkler has a demand pressure of 15 meters of head. The first step is to calculate friction loss. Remember, friction loss can be calculated using a pipe friction table. At 45 liters per minute, and using a pipe 3/4 inch in side diameter, we can see that there will be 40 meters of pressure lost to friction. However, in this chart, all values apply to 100 meters of pipe. In Auntie Flo's case, she only requires 50 meters of pipe. Therefore, we must halve the value. Half of 40 is 20. 20 meters is therefore our friction loss. The next step is to calculate the total head or pressure the pump will need to accommodate. We know that the discharge point is 4 meters above the pump, and the demand pressure of the sprinkler is 15 meters or 150 kPa. We have just calculated that the friction loss will be 20 meters. Add these three amounts together and we have the total amount of head or pressure required, in this case 39 meters. Now we go back and take a look at the pump curve. A pump curve shows what flow rate the pump can produce under varying pressures. This is important to know, so you choose the right pump for your needs. The vertical axis on a pump curve indicates the head or pressure. It's the maximum height the pump can deliver water. The horizontal axis indicates how many liters per minute the model can pump. On the graph, find 39 meters of head on the vertical axis and run an imaginary line across the graph. At the point your line crosses the pump curve, draw another line directly down the graph to the flow rates along the horizontal axis. This is the flow rate your pump can deliver when working against the pressure you have calculated. Is the pump able to produce the flow rate required? In the case of Model A, the answer is no. Let's try the pump curve for Model B. Again, find 39 meters on the head or vertical axis and run an imaginary line across the graph till you meet the pump curve. Then draw a line straight down to the flow rates. Is this pump able to produce the flow rate required at the pressure you require? In the case of Model B, the answer is yes. This means Model B has both the pressure and flow rate to meet Auntie Flo's needs. Don't worry if the flow rate is a bit more than you require. Flow rate is easily controlled at the tap. Let's see what happens if Auntie Flo uses a larger pipe with a 1 inch inside diameter rather than a 3/4 inch. Remember, her requirements will stay the same. We go back to the pipe friction table, only this time we calculate our friction loss using a pipe 1 inch in diameter. We still need 45 liters per minute. We can see that there will be 10 meters of pressure lost to friction. However, as we know, in this chart, all values apply to 100 meters of pipe. In Auntie Flo's case, she only requires 50 meters of pipe. Therefore, we must halve the value. Half of 10 is 5. 5 meters is therefore our friction loss. On our calculations, we change our friction loss from 20 meters to 5 meters. Add these three amounts together and we have the new total amount of head or pressure required. In this case, 24 meters. Let's go back to the pump curve for Model A to see if changing the diameter of the pipe will make this model a viable option once more. This time, we need to find 24 meters on the head or vertical axis and run an imaginary line across the graph till you hit the pump curve. Draw a straight line from this point down to the horizontal axis. By increasing the diameter size of the pipe, Model A can now produce both the pressure and flow rate to meet Auntie Flo's needs. As you can see, pressure will always affect the flow. Another way we can show this is by putting a pressure gauge with a tap on a hose and connecting it to a pump. When we open the tap completely, the flow increases. as the pump is not working against pressure. Watch what happens as we increase the pressure the pump has to work against by slowly closing the tap. The flow rate is reduced. Let's remove some of the pressure and watch as the flow rate increases. Whether the pressure your pump is working against is a hill, pipe friction, hose nozzles, or a partially closed tap, it will all have the same effect on your flow. To find more information on a particular